Good morning. This is Math 0310. It's April the 17th. A couple of announcements. First of all, WebAssign homework. Section 4.7 and 3.5. Remember that 3.5 is from the intermediate algebra textbook. Is due April 24th, so that's next week, next Tuesday. Section 3.6 is due April the 29th, and then 2.7 is due May the 8th, and that's it. Those four sections are the last homeworks out of WebAssign, so we're rapidly finishing up in that respect. After today's lecture, only going to be online for lecture 2 more times for the semester. All right, so this week, kind of a rundown of things that are going on this week. So today, lecture, which is what we're doing right now at 9 o'clock. Online office hours from 11 to noon and from 8:30 to 9:30. Wednesday, tomorrow, I will be on campus. So make sure that you make note of that. Remember that my office is in Winship, 115 K in the North Harris campus. And so I'll be there from 4 to 6 tomorrow afternoon, and on Thursday from 9:30 to 11:30 in the morning. So please come by for help if you need it. Going into exam 3, I'll be happy to help you out with things if you have questions on the review. So please come on by. The exam 3 window, remember, opens tomorrow. No, I'm sorry, it doesn't open tomorrow. It opens Thursday, April the 19th, and goes through the 24th. And then Friday, Saturday, and Sunday this weekend, you can make online hours by appointment. Just text me or email me. Text me through Remind or email me, and we'll see if we can set up a time sometime that's mutually agreeable where we can go over some homework or something some questions you've got from the review. I'll be happy to meet with you online in my WebEx office. So let me know that. Sunday, I do have my regular online office hours from 8:30 to 9:30 in the evening. One other thing to mention here is that there is a final exam review, and that review will go up. I will be posting it on my Google site sometime probably later this week, just so you know. You've got a while before the final exam actually opens up, but I will definitely get that review online probably later this week. So if you don't see it by the end of the week, you might send me an email to remind me about it, but I'll try to get that review up and running by then. All right. So today, what we're going to be doing is we're going to be talking about more on graphing functions, and then we're going to start in on basically the last topic of the semester, which is inequalities. In particular, we're headed to absolute value inequalities and equations, but we need to do some work with inequalities in one variable, compound inequalities in one variable, and so we'll spend some time working on those things for the rest of class today. Like Taylor and I were just talking about before I actually started this video, this material is on the final exam only. This is not on exam 3. So this material is not on exam 3, but will be on the final exam. Exam 3 stops with the basic things we were talking about with functions, function notation, finding domains and ranges from graphs of functions, things like that. So this is all now geared towards the final exam, basically, is what we're talking about. Okay, so more on graphing functions. That's our first stop here. And this really will be a little bit of a review of some things that you do need to be able to deal with on exam 3 also as we go through this discussion on graphing functions. So we started talking about this last time, and so I want to continue on with this. First of all, just some basic functions that you should be able to identify by name, and then also their graphs. So f of x equals 2, for example. When you have just a constant for the function, this is actually called a constant function. Here we have f of x equals 2. It's called a constant function. No matter what the x value is, if we were using function notation, your answer is always 2. So f of 3 is equal to 2. f of negative 5 is equal to 2. F of 10 is equal to 2. And so on. Right? This kind of function is called a constant function. Also, don't forget what f of x is another name for. F of x is another name for y. And so when I write f of x equals 2, I'm really writing the equation y equals 2. And we know that a function or an equation like that, y equals a constant, its graph is a horizontal line. All right, so constant functions always have graphs that are horizontal lines. Okay, so in this case, y equals 2 or f of x equals 2 would have a graph that looks like this one right here. Right, goes through 0, 2 right there. Okay, and one thing, and this will be a help going into exam 3, if you're talking about the domain and the range for that graph, right, the domain for that graph is all reals, right, that no matter what x value you use, so in words, all reals, but no matter what x value you use, remember how we talked about doing this when we were dealing with domains and ranges from graphs, was we talked about walking from left to right on the x-axis and looking vertically to see if you see the graph. Well, a person who's doing that, walking left to right on the x-axis, is going to see the graph everywhere. And so if you're shading the domain's going to be the entire real number line right here. And so constant functions always have a domain that's all reals. The range is a little bit different. The range, remember, now you are going up the y-axis and looking for the y values that are on the graph. But with constant functions, incredibly, or I don't know if it's incredibly or not, but there's only one value in the range, and that's 2. You wouldn't even use the interval notation here. You just write the number 2 and put it in braces. That's the only number that's in the range for that function. Constant functions always, always, always behave like this. The domain will always be all reals. The range will always be just a constant, just one number. The graph is always a horizontal line. So when you walk into college algebra, your professor's talking about a constant function, you should be able to identify a constant function like that. All right. The next type of function, we have f of x equals 3x minus 1. And this is called a linear function. Right? We've talked about these. We know that a linear function, again, remember that f of x is another name for y. So this is y equals 3x minus 1. And we know that the graph is a line. You could certainly plot points here if you wanted to. That wouldn't be a big deal at all if you chose to do that. There's multiple ways you could graph this function. In particular, what we've talked about some is x and y intercepts, but let's look at function notation here for a minute. So f of 0 would be negative 1, right? You're just substituting 0 in place of x. So you have the point 0, negative 1. F of 1 would be equal to 2. When you substitute 1 in for x, you get 2 for y. So you get the point 1, 2. F of 2 would be 5. When you substitute 2 in for x, you get 5 for y. So the graph goes through the point 2, 5, etc. So you should be able to use function notation to generate points. You should also be able to find the x and y intercepts for any basic function like the ones we're talking about. So if you have, for example, the x and y intercepts for this graph, the x-intercept, remember you're substituting 0 in place of y, so you get this equation, 0 equals 3x minus 1, and then add 1 and divide by 3, and you get x is 1/3. And so the x-intercept's at 1/3, 0. The y-intercept, you know you're substituting 0 in place of x, and you know the graph's in, or the equation's in slope-intercept form, so you should be able to tell from that anyway, but substituting 0 for x, you get y equals negative 1. So the y-intercept's at 0, negative 1. All right, so those are the intercepts. You should be able to sketch the graph of a function like this without any problem, either by plotting points, by finding the x and y intercepts, by using the slope and the y-intercept. Those are all ways you could deal with a linear function. So 1/3, 0. I'm going to make the scale different here. I'm going to make that 1 right there. And so that would be -1 there. And so the y-intercept is at 0, -1. The x-intercept's at 1/3, 0. And here's our graph. Okay, so on this function, as far as the domain and the range, once again, a little bit of practice with the domain and the range. With slant lines like this one, as a person's walking along the x-axis, when they're looking vertically, they will always see the graph again, always. And so the domain for f in this case is going to be all reals. Slant lines always have this domain. Always. All slant lines have a domain of all reals. And then the range for this function, the set of y values, as a person is climbing up the y-axis, going from bottom to top, and they're looking left and right in this case. And once again, this person would always see the graph. And so the range is all reals also. Domains and ranges for slant lines always are both going to be all reals. That will always, always, always be true. All right, so this will always be the domain and range for any slant line. And when I say a slant line, remember, I'm just talking about a line that's not vertical and not horizontal. All right. So that's an example of a linear function, kind of going back over some function notation stuff, some domain and range stuff, and also finding intercepts, things like that. All right, the next kind of function that we started looking at is actually, let me write it more generally. I did not write it out this way last time, but it's second degree function like this one, right? A linear function is a function that's in this form, ax plus b, right? That's linear. Those graphs are lines, right? It's a first degree equation, right? Because the x is raised to the first power. This is a second degree equation, and this is called a quadratic function. Now, for those of you going on to take college algebra, you'll look at quadratic functions in much more detail than what we're about to do right here. But the graph on this type of function, the graph is always a parabola. And what I'd like you to be able to do with a quadratic function is I'd like you to be able to find x and y intercepts. That's something I would want you to be able to do, is to find the x and y intercepts. And I'd also want you to be able to graph by plotting points. And then from the graph, write the domain and range. And the domain and the range is actually good practice for stuff from exam 3. So, okay, so now plotting points is not always a good method for graphing a quadratic function. We're only going to look at ones where finding or plotting points would be an appropriate way to sketch the graph. Okay, we're not going to look at the ones where plotting points is not going to give you enough information to sketch the graph at all. All right, so let's look at a couple of examples of quadratic functions. So if I have f of x equals x squared minus 4. First of all, on a function like this, I would like you to be able to find the x and y intercepts. So the x-intercepts. Remember how you find the x-intercepts. Don't forget that f of x equals x squared minus 4 is the same thing as y equals x squared minus 4. Those are the same equation. So the x-intercepts, you're going to set y equals 0. And so you have 0 equals x squared minus 4. And notice what happens with a quadratic function. When you're looking at the x-intercepts, you always end up with a quadratic equation. And so you've got to solve that quadratic. So this one factors x plus 2 times x minus 2. So that would be one way to solve that. And you set each factor equal to 0. And you get negative 2 and positive 2. And so this graph has two x-intercepts, one at negative 2, 0, one at positive 2, 0. Now, a quadratic function does not have to have two x-intercepts, but typically they do. Definitely don't have to, and you'll see that as we go through this. The y-intercept, you set x equals 0. And when I set x equal to 0 in my equation, I get y equals 0 squared minus 4. So y is just equal to negative 4. And so the y-intercept's at 0, negative 4. Now that's enough information right there where you could make a decent sketch of the graph. I'm going to go ahead and find a couple of more points here. Okay, so I'm going to use this set of points that we've talked about. And you can judge based on the problem whether this is enough points or not. So you've got x is negative 2, negative 1, 0, 1, and 2. And we've actually already found some of these values by looking at the intercepts. Remember that f of 0, because that's x equals 0, that's always going to be the y-intercept right there in that point when x is 0. So you're looking at f of negative 2, f of negative 1, f of 0, and so on. So you get 0, because we've already got that one from above. When x is negative 1, you have negative 1 squared minus 4, or negative 3, because that's 1 minus 4. 0, well, we already know that's negative 4. 1, you get 1 squared minus 4, and so that's also negative 3. And at 2, you get 0. We already got that one. So our graph looks like this. Let's have a look at the graph, and then we'll write the domain and the range from that graph. So the y-intercept is down here at 0, negative 4. The x-intercepts are at 2, 0, negative 2, 0. And we've got the additional points of negative 1 and positive 1, negative 3. Right, so we get those points right there, and so we have a pretty good picture of our parabola here. All right, so there's the graph right there. Okay, so let's talk about the domain for this function and the range for this function. The domain and the range. Now the domain, you're talking about walking along the x-axis and looking to see if you see the graph vertically. But this graph is always spreading out because of the way the arrows are drawn there. This graph always spreads out and it's going up both. And so the domain here is going to be all reals. And this is always true for quadratic functions. Quadratic functions, just like linear functions, the slant lines, the domain for these is always going to be all reals. Now the range is not all real, so you got to be careful here. So with the range, I'm climbing up the y-axis, going from bottom to top. And this person is looking left and they're looking right to see if they see the graph. And so the first place this person sees the graph is right here at negative 4, and then they see the graph 2 times actually, left and right, all the way up like that forever. So the range is going to be bracket negative 4 to infinity in interval notation like that. And that's the way I'd want you to write it, is in interval notation. And so from the graph, we can tell that the range here is going to be from -4 to infinity. So it's a little bit different range in this problem. Okay, next problem. So for those of you who are with me live, please don't hesitate to stop me as we're going through this. Okay, so next problem, we have f of x is equal to, let's say we have negative x squared. Let's say we have 10 minus x squared. That's what I'm going to do first. 10 minus x squared. Okay, so first thing I want to do is I want to find the x and y intercepts for this function. So the x-intercepts. We set y equal to 0. Right, and so we get this equation, 0 equals 10 minus x squared. Don't forget that this equation is really y equals 10 minus x squared. So you get 0 equals 10 minus x squared, which is a quadratic equation, but you can't factor it. It's not factorable, but you can add x squared to both sides. And then you use the square root method to solve this, and you get x is plus or minus the square root of 10. And those are the x-intercepts. There's nothing wrong with those values being the x-intercepts. We would estimate those. Those are about 3.1 and negative 3.1. So if you're going to use them on the graph, that's what you're going to get. All right, so our x-intercepts are at negative square root of 10, 0, and positive square root of 10, 0. And those points are at about negative 3.10 and about positive 3.10. So those are kind of estimates that we can use when we're graphing. All right, the y-intercept. The y-intercept, we substitute 0 in place of x, so you get y equals 10 minus 0 squared, and so you just get y equals 10. And so our y-intercept's at 0, 10. All right, so those are my intercepts. And then the next thing I might want to do is I might want to just plot some points. And in this case, generally speaking, we don't have any of these. We have one of these points and that's it. So let's see what we've got here. We make a little table of values. And we'll try -2, -1, 0, 1, and 2. You know, you'll have to judge each problem on its own merits as far as whether those are appropriate. And you'll know when you're plotting points whether these are appropriate or not. All right, so when x is -2, you're looking at f of -2, which is 10 minus -2 squared. Please be careful of the signs here. That's 10 minus positive 4, or 6. So f of -2 is equal to 6. F of -1 is 10 minus -1 squared. So that's 10 minus positive 1, that's 9. F of 0 is easy because I've already found that one, but I'll write it out again. That's 10 minus 0 squared, which is 10. F of 1, notice that it doesn't make any difference whether I use positive 1 or negative 1. I get the same answer here, so this is going to be 9. And then f of 2 is the same as f of -2. I'm going to get 6 right there. All right, so my graph, I'm going to make the scale a little bit bigger here, or just to make it a little bit bigger numbers as far as the y values go. So the intercepts, we know, so we got a lot of points here. Intercepts are just a little bit past -3 and positive 3, just outside of -3 and positive 3. The y-intercept's at 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, way up here. There's our y-intercept. And then we have points at -2, 6, 1, 2, 3, 4, 5, 6, -1, 9 up here. Then we have 0, 10, and then positive 1, 9, and positive 2, 6. And we get those points right there. And so we've got definitely got enough points to make a good sketch of the graph here. And so here's my parabola. All right, the domain for this parabola. So the domain for f, and like we talked about in the last example, the domain is going to be all reals. All x values are in the domain for any quadratic function. That's always going to be true. The range on f is not going to be all reals, right? As this person is climbing up the y-axis, they're looking left and right, and they see the graph. And if you look at it, they see the graph until they get all the way up here to 10, and then they stop seeing the graph right there. So the range for this function is going to be at negative infinity. It goes all the way down, so negative infinity to 10, and then we close the brackets like that. Right? Remember, it's always going from bottom to top. So going down here, this is negative infinity, going in down on the y-axis like that. All right, so there's a sketch of the graph. All right, let's see. Let's look at some more problems here. We have f of x equals x squared minus 4x. So this would be an example of definitely of a quadratic function. If we are looking for the intercepts, the x-intercepts, remember that this equation is y equals x squared minus 4x. And so the x-intercepts, you substitute 0 in place of y. And then this is a factorable quadratic expression. And so you end up with x equals 0 and x equals 4. So the intercepts for this function are at 0, 0, and at 4, 0. Right? The parabola actually goes through the origin. The y-intercept, well, 0, 0 was the x-intercept. You're going to get 0, 0 for the y-intercept on this problem also. All right, so you could go through here and plot some points and see what happens when you plot points. And see if you've got enough points to make a decent sketch of the graph. Here's our coordinate system. Whoa. We know that this graph goes through the point 0, 0 and 4, 0 like that. So if you used our little familiar set of points here, -2, -1, 0, 1, and 2, right? Then you're looking at f of -2, f of -1, f of 0, f of 1, f of 2, and so on. So let's see if that's enough points here. So f of -2, again, an easy place to make a mistake. This is -2 squared minus 4 times -2. And so you get positive 4 plus 8, 4 plus 8, or 12. So at -2, you're all the way up at 12. At -1, you're at -1 squared minus 4 times -1. So that's 1 plus 4, or 5. Okay, f of 0. We've already done f of 0, but you get 0 squared minus 4 times 0, and you get 0. F of 1, you get 1 squared minus 4 times 1. So it's 1 minus 4, or -3. F of 2 is 2 squared minus 4 times 2, so that's 4 minus 8, or -4. So let's see what we've got so far, and let's see if that's enough points. So you have -2, 12. Let's see, I don't even know if I can fit this on my screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So -2, 12 is way up here on the edge of the screen. And then negative 1, 5. 1, 2, 3, 4, 5 is right here. And then you've got 0, 0. And you've got 1, negative 3 is here. And 2, negative 4 is here. So notice this is a graph where you might want to go on to 3 and get x, what happens when x is 3. So when you have f of 3, you get 3 squared minus 4 times 3, which is 9 minus 12, or negative 3. See, now it starts making sense. So that gives me 3, negative 3 is this point right here, and now you can start seeing the parabola. Right, and you've got these mirror image points if you want to use that idea here, because you can see that this graph's going to have symmetry, but you don't have to worry about that too much here. So here's our graph, like so. All right, and so the domain for this function, remember we've already talked about that the domain is all reals for all quadratic functions. And the range, as you start looking for the graph as you're going up the y-axis, right, you start seeing the graph here at negative 4. And you see it for every x value above negative 4, like that. And so the range is going to be from negative 4, bracket negative 4 to infinity, like that. All right, so far doing good, doing good. Just a couple of more examples. We're not going to look at graphs on these. Let's just look at x-intercepts. So you have f of x is equal to x squared minus 2x minus 48. F of x is equal to x squared minus 2x minus 48. All right, so on this function, if you were just find intercepts only here. Find intercepts only. So the x-intercept, or intercepts, we know that we would substitute 0 in place of y. So you have 0 equals x squared minus 2x minus 48. And then you hope that that factors. By the way, if it doesn't factor, then you would use the quadratic formula to find the x-intercepts. That's definitely a possibility. So you have 0 equals x minus 8 times x plus 6. And you set each of those factors equal to 0, and you end up with 8 and negative 6 as the intercepts for the x-intercept. So you have 8, 0, and negative 6, 0. And then the y-intercept, you substitute 0 in place of x. So you have 0 squared minus 2 times 0 minus 48. And that's pretty easy because you just get 0 for the first two terms. And so the y-intercept's at 0, negative 48, like that. All right, and so that would be those are actually enough points that you could make at least a semi-decent sketch of the graph. It's not a completely good graph here, but it's at least you could get a semi-decent sketch of the graph based on those 3 intercepts. And you can certainly plot points to find some more points on the graph there. All right. Next problem I want to look at, let's look at this function. Let's say we have f of x is equal to f of x is equal to x squared plus 4. X squared plus 4. All right, so when you find the x-intercepts here, you're substituting 0 in place of y, so you have 0 equals x squared plus 4. And then you subtract 4, and you're going to use the square root method to solve this equation. The problem is when you take the square root, you get plus or minus the square root of negative 4, which is imaginary. You get plus or minus 2i for x. You cannot have imaginary intercepts. Those are not points on the coordinate plane that we use. And so when you have imaginary solutions here, you are saying no real solution. Right? There's no real solution to that equation, and it means there are no x-intercepts for this quadratic function. A parabola does not have to cross the x-axis. This one doesn't cross the x-axis. The y-intercept, that one's much easier. You get y equals 0 squared plus 4, so you just get y equals 4. So our y-intercept's at 0, 4. All right, so you would definitely want to plot points to make a decent sketch of this graph. I'm just going to run through with you briefly here that f of 1 is equal to 5, and f of negative 1 is also equal to 5. F of 2 is equal to 8, and f of negative 2 is also equal to 8. And so that would give you, those points would give you enough information to sketch the graph. Right, this graph has a y-intercept here at 0, 4. And it goes through 1, 5, and negative 1, 5, like that. And 2, 8. And negative 2, 8, like that. And you have this parabola, and you can see why it does not have any x-intercepts. Right, the graph is always sitting above the x-axis there. Like that. So no y-intercepts at all. Definitely a possibility. All right. Next problem I want to look at with plotting points. We want to move away from quadratic functions, and let's look at a square root function. So let's say we have the square root of x plus 4. F of x is the square root of x plus 4. All right, so when you start trying to plot points here, what I want you to notice is this. And so we're going to have to plot a few more points than we might ordinarily do to see what I'm talking about here. But first of all, when x is 0, y is the square root of 4, because it's 0 plus 4, so that's 2. When x is 1, you have the square root of 1 plus 4, which is the square root of 5. That's okay to have a square root like that as a y value. You just have to estimate that. When x is 2, you get the square root of 2 plus 4, which is the square root of 6. The next x value that gives you a nice y value back is 5. When x is 5, you get square root of 5 plus 4, or the square root of square root of 9, which is 3. When you go back with negatives, when x is negative 1, you get the square root of negative 1 plus 4, which is the square root of 3, which is approximately 1.7. Square root of 5 is approximately 2.25. When you use negative 2, you get the square root of negative 2 plus 4 is the square root of 2, which is about 1.4. A little bit bigger than 1.4. I'm going to extend this table. When you get negative 3 for x, you have the square root of negative 3 plus 4, which is the square root of 1, but that's 1. And when x is negative 4, you get the square root of negative 4 plus 4, or the square root of 0, which is 0. And then what I want you to notice is that if you try to use negative 5, that the square root of negative 5 plus 4 is the square root of negative 1, that's imaginary. And so we say that negative 5 is not in the domain. Not in the domain. Negative 6 is the same. You know, all these x values that are less than negative 4 are not in the domain for this function because you get imaginary y values back. And so the graph for this function, I'm going to put it above right here. Let's see, we have negative 4, 0 right here. And then we have negative 3, 1. And 0, 2. and 5, 3. Like that. And we could fill in the gap with some of those decimal values if we wanted to. This graph is actually the upper half of a parabola that opens to the side, like that. And that's the graph. That's a common type of graph for a square root function like that. The domain for this function starts at -4 and goes to infinity. So the domain is from -4 to infinity. And the range is from 0 to infinity, like that. And graphs like that are typically what you're going to get when you have the square root, especially if you have the square root of a linear expression like that, you're going to get a graph that looks like that one. All right, so we've gone through a lot more stuff about graphing functions. In particular, x and y intercepts, I really wanted to look at that. And so now what we're going to do is, and this still has to do with graphing, but we're going to leave graphing in the plane behind and go back to one variable statements. So to finish the semester, we go back to looking at one variable equations and inequalities. So if we're talking about one variable, when we talk about the graph, in this case, the graph is on a number line, not on the coordinate system, but the graph is actually on a number line. And so we're talking about graphing on number lines again rather than in the plane like we have been for the last few days of the semester. All right, so we're talking about one variable only. If we look at a very simple inequality, x greater than or equal to 2. Gee, that's incredibly simple. On a number line, what are we doing? We're talking about all the x values that are bigger than or equal to 2. So if there's 0 on the number line, there's 1, there's 2, there's 3. We're talking about all the numbers that are greater than or equal to 2. So 2 would be a solution, and all the numbers on the number line to the right of 2 would be a solution. And so this would be a graph of the solution set. It would look like that. Everything from 2 to the right. And an interval notation. So we started talking about interval notation now. On that particular problem, the interval starts at 2, but then doesn't stop in the right direction, and so we use an infinity symbol there. We put a bracket around the 2 to say that the 2 is included, and we always put a parenthesis around the infinity, remember. And so that's the solution in interval notation. So all we're doing is practicing graphing statements like this. All right, the next example, let's say we have -3x plus 8 is greater than let's say -4. All right, so first thing you do is solve this inequality. So you get -3x is greater than -12. Just subtracted 8 from both sides. And then divide by -3. And don't forget, when you divide by a negative and an inequality, you reverse the order symbol. So I'm dividing by a -3, and so I reverse the order symbol, and I get x less than 4. So please don't forget that. Easy to forget that when you're dividing by a negative, that you have to reverse the order symbol. So this becomes x less than 4. Okay, so on a number line then, x less than 4. So if that's 0, There's 1, 2, 3, 4, 5, like that. And this problem 4 is not part of the solution set because this is x less than 4. So we put an open circle around the 4. And since it's less than 4, we are shading to the left in this case on the number line. And so that's what the solution to our inequality looks like on a number line. Those are the solutions. And in interval notation, the left edge of the interval would be negative infinity. Don't forget this is always negative infinity and this to the left, positive infinity to the right. So this is negative infinity to 4. We put a parenthesis around the negative 4, the negative infinity. We also put a parenthesis around the 4. Okay, so, and that would be the solution set in interval notation. All right, next problem. Now the next problem is an example of what we call a compound inequality. X less than negative 2 or x is greater than or equal to 3. This is called a compound inequality because it has two order symbols in the same statement connected with the word or. The word or simply means that one of them has to be true but not both of them, right? So the or means one has to be true but not both. In this case, there are no numbers that are both less than negative 2 and greater than or equal to 3. Right? But it doesn't have to be both because of the or. So on a number line, we actually have two pieces to this graph. So let's say if this is 0 right here, so here's negative 2, here's positive 3. And so we're talking about all the numbers less than negative 2. So we put an open circle around the negative 2. And x less than negative 2 means we're shading everything to the left from negative 2. 3, on the other hand, is in the solution set because it's greater than or equal to. So we put a solid dot there. And then we shade everything to the right of 3. So this type of compound inequality actually has two pieces to it when you graph it on a number line. And in interval notation, you actually have to write two pieces to the interval notation. You write negative infinity to negative 2 for the first piece, parenthesis around the negative infinity, and also a parenthesis around the negative 2 because of the open circle there. And then with the everything to the right of 3, you'd write 3 and then infinity. 3 would be on the left, infinity would be on the right, just like the shaded part is like that. The 3 is included, so we put a bracket there around the 3, and we put a parenthesis around the infinity. And when you have to use two statements like this, you connect them with a union symbol to make it into one statement. And so that would be the solution set for that inequality, both as a picture on a number line and in interval notation. Okay. So the next example, let's say we have 2x plus 1. Let's say negative 2x plus 1 is greater than or equal to 5. Or 3x plus 2 is greater than or equal to 11. All right, so that's also a compound inequality. This is an or statement. And so what you do is you first solve each inequality just separately. So in the first one, you subtract 1. So you get negative 2x is greater than or equal to 4. And then divide by negative 2. You have to reverse the order symbol. So this becomes x less than or equal to negative 2. And then the other inequality, so solve for x there, you get 3x greater than or equal to 9. Divide by 3, you get x greater than or equal to 3. And so as an inequality, that would be the solution set right there. All the x values that are less than or equal to -2, or any x values greater than or equal to 3 would be solutions that would satisfy that original statement. Now in a number line, that's 0, here's -2, and here's 3. And so you have everything less than or equal to -2. So on a number line, we've talked about all of these values, and everything greater than or equal to 3 would be all of these values. This would be another set that comes in two pieces like this. And so in interval notation, you'd have to use two pieces here. This would be -infinity to -2. You'd close the brackets, union 3 to infinity like that. I mean, that would be the solution in interval notation. All right, the next one's going to be different. This next one is x plus 1 is greater than or equal to -4, and x plus 1 is less than or equal to 8. Now, this is an and statement, and so the only x values that make this one true are x values have to make both statements true in order to be solutions. X's must make both small statements true. In order to be a solution to the big statement. All right, so now what I want to do is I want to point out to you, if you have x plus 1 greater than or equal to -4 and x plus 1 less than or equal to 8, that this x plus 1 greater than or equal to -4 could be turned around as -4 less than or equal to x plus 1, and x plus 1 is less than or equal to 8, like that. And then that statement, notice it's an x plus 1 in both inequalities. That's the same expression. And with and statements, we frequently, in fact, most of the time, combine the and statements into one statement like this with two order symbols in it. And we typically write an and statement as -4, like this, -4 less than or equal to x plus 1, which is less than or equal to 8. Now, this cannot be done with or statements, can only be done with and statements. So can only be done with and statements. And what that statement at the end means is you're looking for the x values that satisfy both x plus 1 greater than or equal to -4 and x plus 1 less than or equal to 8. Now, to solve this type of compound inequality, you simply just subtract 1 from all three parts of the inequality. And so you get -5 less than or equal to x, which is less than or equal to 7. This is all the x values that satisfy the statement that they're both greater than -5 and they're less than 7. And if you think about that for a second, what you get is you get all the x values that are between -5 and 7 have to be solutions to this inequality. Put 7 right about there. X values between -5 and 7 make this true. When I say make this true, they make both statements true. That's what you're looking for, are the numbers that make both statements true. And that ends up being all the numbers between -5 and 7. And because both of those have equal to's on them, we put solid dots there. And so this is actually really different. This is actually an interval here. And the solution set in interval notation would be all the x values between -5 and 7, and we would close the brackets like that. It would be a nice definite interval. All right, this is the most common form. When I say this, I'm putting a red box around it here. This is the most common form for a and statement, is to write it that way. That's simply an abbreviation for that statement like that. It's an abbreviation. You cannot do this with or statements, but you can do this with and statements. All right, so let's look at, and this may be kind of our last problem of the day. We're close to it at least. So let's say we have -6 less than 4x minus 3, which is less than or equal to 8. Like that. Okay, so this is, because of the way this is written, this is an and statement. This is that abbreviated form for an and statement. And it's actually 4x minus 3 greater than -6, and 4x minus 3 is less than or equal to 8. It's an abbreviation for those two statements connected with the word and. But the good thing is, with the abbreviated form, all you have to do is get the x by itself in the middle there. So you add 3 to both sides, you get -3 less than 4x, which is less than or equal to 11. And then you go through and divide everything by 4. And so you get -3/4 less than x, which is less than or equal to 11/4. And by the way, 11/4 is 3 and 1, 2 and 3/4. 4 goes into 11 twice. So 2 and 3/4. All right, so on a number line, this would be all the numbers between -3/4 and 11/4. So if this is 0, and let's say, let's make this scale a little bit bigger here so we can get this a little bit more accurate. There's -1. So this is +1, +2, +3, like that. So -3/4 would be located here. And +11/4 would be 2 and 3/4 would be here. Okay, so on a number line, we put an open circle around the -3/4. We put a filled in dot at the 11/4, and we would shade everything in between like this. And this would be a picture of the solution set to this inequality. It's everything in between like that. And in interval notation, the solution set would be from -3/4 to 11/4. We'd put a parenthesis around the -3/4 because of the open circle. We'd put a bracket around the 11/4 like that. All right, so now one thing to point out to you is this x and y intercept stuff. Not as many problems in the book as I would like for practice on that. So if you're looking for practice finding x and y intercepts with linear and quadratic functions, these problems would be good practice right here. And so I will, I'll post the solutions on these later, but I'm going to include these in this homework, and this would be, or in these lecture notes. And so these would be good problems to look at for practice, because there's not enough of these kinds of problems in the textbook. So these will be at the very last page of these notes. Okay, so exam 3 starts Thursday. You have a great review online. Take advantage of that review. Work as many problems on that review as you can without any help, without any notes or book or anything. Don't hesitate to call me, email me, send me a remind message, a web assign message. You have multiple ways to get in touch with me if you have questions. Please try to come by on campus hours this week on Wednesday and Thursday. Remember, you can also make an appointment sometime on Friday, Saturday, Sunday for online hours as well. So good luck as you're going into exam 3. Let me know if there's any way I can help.
Okay, thank